All right, hi. So, my name is Kristinn Gudjonsson, and I'm here with Johan Berggren, and this is our take two because we had a minor adapter issue, but we got our backup laptop and backup adapter. So today, I'm going to talk to you a little bit about how to get your data to talk. How do you get your timelines and your data to really talk to you? But before we go there, I just wanted to go a little bit, talk about the current state, where we are right now. So you start thinking about it. We have our disk images where we can get all the data from, right? Registry information, event logs, syslog, agent logs, or we can start collecting files and start building up our super timelines. Then we can move on to the network where we have our IDS, we have our IPS, firewalls, all that stuff. Then we go to the server side where we have our server logs, services logs, and so on and so on. And we can add more data to it. But the end result is we just got too much information. We just got too much data to go through, line by line and reading it up. And that's why we, as forensicators, we tend to try to find some sort of pivot points. We have whether the pivot point is some sort of event that we know happened, it might be a point in time, or it might be some keywords that we have. We just have something that we are using as pivot points into our data set, and then we go from there. But the end result is the same. We get just too much data to look through all manually, so we need some sort of either methodology or tools or something to help us find those true rare gems we're looking for. So you might be asking yourself, hey, with all this data, is there any hope? Well, if I wasn't trying at least to present something here, it would be a shitty presentation, so let's assume I'm at least trying to convey a hope. Another word of warning is that this talk will contain a lot of buzzwords, so I hope you forgive me, especially if I give you a warning ahead of time. So the first buzzword of the day is really data science, and that's really what I wanted to talk to you about today. If you actually go look it up, data science is obviously a buzzword, but it's also a kind of convoluted term because it means a lot of things. So if you go look it up online, you will find multiple different definitions of what data science is and isn't. And a lot of confusion between statistics and machine learning specialists, data architecture, whatever they call it. Here I'm just putting up a definition from Wikipedia, which may or may not be perfect, but it is what it is. But it really boils down to data science, at least the way I look at it, it's a way to extract insights from both structured and unstructured data. And then we have a blank slide. So if we start looking at data scientists, which is the person that does data science, they are really, you can kind of look at them as unicorns. They're magical. They might not really be real, but they're definitely rare, right? Because they are supposed to know it all. They are supposed to be expert statisticians. They're supposed to know everything about probability theory, machine learning, AI, big data. They're supposed to be able to know everything about visualization and be able to present data to business deciders. But they're also supposed to be expert in the actual data that they're looking at, which means that they have to be expert in forensics today. Then tomorrow they might be called in to do, factor line optimization, and they need to know everything about that. And that's really where we come in. So we start looking at, the people in this room. We are the expert forensicators. We've been looking at this for, many, many years. We might even have, the data science part, the computer science part as well. We might be doing some programming. And we tend to convey a lot of technical information to non-technical people through our reporting. So we already have a lot of these building blocks to make up for a data scientist. All we're really missing is just the data science part. But I think, it's easier for us often to start learning at least the fundamentals of data science. You don't have to be, data science to really benefit from it. It's a field on its own that takes years to master, but even knowing just the fundamentals, the basics of data science, can really help you become better at forensics. And that's kind of what I really wanted to talk to you about today. And if we start comparing, data science and forensics, and we start comparing these two things and looking at, is there anything in common there? We start thinking, if you go back to our definition, data science is all about extracting knowledge from structured and unstructured data, which is exactly what we do. Data scientists are also obsessed over anomalies in the data sets. They tend to throw them away because they're looking at trends or big picture view, whereas we're just looking for the anomalies because that's our bread and butter. They also tend to do a lot of things with clustering, as in they are trying to figure out behavior in the data, same as we. Or we could be looking at trends. So what I'm saying is that there are actually a lot of things in common with these two fields that we can start using to our benefit. So if you start thinking about it, what can we really gain from data science? So one of the big things that happened, in the past, 5 or 8 years, with the explosion of buzzwords, big data, AI, ML, data science, all that stuff, is that lots and lots of tools were developed. And tools that we can really use and benefit for our benefits. Also, they did a lot of enhancement to methodology for data exploration, which is basically what we do when we're doing analysis. And another thing one of the key things about data science is that it's really all about, visualization. They're taking this big data, you have this big data set, and what you're trying to do is you're trying to extract some knowledge out of it and present it visually to a business decider that can then take that data, understand it, and then make informed business decisions. Which means also that there's a lot of tools now there for visualization. Great libraries and others that we can use for our benefit. And it's also proven that it's much easier for us humans to spot both anomalies and trends in the data set if you look at it visually, rather than just catting a log file and hoping for the best. Aggregation is also a big form of that, and we can use that to get to know our data set. So you can start thinking about how do we start using it? What can we really do to start doing it? So one of the things that really exploded in this phase was that languages like R and Python became very popular in the age of data science, and most notably for their use of the interactive notebooks. I mean, they had a way where you could interactively use these notebooks and then get feedback immediately for data exploration. So what we have is that we have Jupyter, which is basically the continuation of the old IPython notebook. And then we have other variants out there like Colab, which is built on top of Google Drive and can allow collaboration and so on. And there are many others out there. It basically uses standard Python, which means that you kind of have to know Python to be able to use it properly. But that's about it. So you might be asking yourself, hey, can I start playing around? How can I look at this? So if you go to our GitHub page for Timesketch, github.com/Google Timesketch, you will find the README file there. If you scroll a little bit down, you'll see 2 little icons there, Launch Binder and Open in Colab, and you just click these buttons, and it will open up either a VM with Jupyter Lab, or just open up directly with Colab, and you can just immediately start playing with it. We have some demos which you can walk you through how these things work. I also want to do a little bit of live demo, which as they should probably fail. But I did pre-run it before here, so I know it actually works. You can also fetch the notebook if you want to take a look at it, because it's very long, and I'm not going to go through it all here. So basically what I wanted to show is that I wanted to show, wow, in a text that you can't really read. But a notebook, like this is a Jupyter notebook. It's basically a mix of markdown text and code. So you can actually write your reports using this as well if you want to. Or you can at least write what are you doing and some interpretation of it. And you can use it as a case log later on to see every command that you ran, every output of it, and so on. But in this case, we're looking at a demo data set that we had. And this is a compromise investigation. And we wanted to know, hey, is there any chance that the user got sent or went to a phishing domain? And in that case, we started looking at, okay, what is a phishing domain? We started defining that as, it's probably something that is similar to our domains. So let's look at similar domains. So what we do here, we start importing libraries, we start reading the data, I'm not going to go through any of this. I start exploring the data a little bit. I also see that the data doesn't really have a domain field, but it has a URL field. So I have to start extracting the domain, which is what I want. And then, to compare, if I want to see something, whether it's similar or not, I need to have something to compare against. So I start with, what are my corporate domains? So I have a list of corporate domains. And then I take a look at, okay, I'm going to go and I'm going to add in the most frequently visited domains of this particular user. Just to this timeline, what are the domains that this user most frequently visited? And add that into that list. Because it's most likely that they're not visiting their phishing domains most frequently. So that means that we have a list. What we do then is we calculate a min hash value. Basically what happens is that we take the domain, we split it up in a set of characters, and then we calculate a min hash value. And then we can use that to compare against other domains using Jaccard distances. We don't really have to know all of this stuff, but it's just a simple statistical probability of two sets being the same. So we do that. We go through each and every domain in the timeline, and we just compare it. And then we find and we see some domains that are similar. And the one that pops up immediately is the domain Grendale, which is very similar to Greendale, which is our corporate domain, which is then the phishing domain. And then we can start looking at this visually if we want to, and so on. I also want to just quickly go over, we also have a pretty robust Timesketch API, where you can, if you upload all the data into Timesketch, you can start interacting with it and looking at it. You can do everything you can do in the UI using the API in Colab or in Jupyter. And I have some demos here. You can just go through them if you want, just to show you how and when and how this UI works. So if we move on, really what, the end result is that here is that you don't really need to become a statistician or probability expert really to be able to, gain benefits from data science. And you kind of often just need to know what you're looking for, and then look at your data set, and then you might have to just extract something. You might have to extract the login type or the domain or something like that, and then just do count. If you just look at executions, you can build an execution tree and then just say, how often have I seen this? Oh, this is the first time? Might be bad. But it's also a great way, doing the exploration and just getting to know your data, doing aggregation, looking at the data set, and that's a great way also to find out anomalies and other stuff. And sometimes also just learning a new field can really benefit you. So with that, I'm going to hand the baton over to Johan to continue with this.
All right. Thank you, Kitty, for the magical unicorns. Can you hear me well? Yeah. No? No. All right. Should I do this? Yes. Okay. Thank you, Kitty, for all of the buzzwords and the magical unicorns. What I'm going to talk about is how can we take this research and how can we take the insights from this data exploration into real world? Because at the end of the day, I want to be able to use this in my investigations, right? And I guess you too also want to do this. So I'm going to talk about that. When Kitty approached me with this idea about, hey, I'm doing this research on our data, how can we use this for our day-to-day jobs? I got pretty excited about that because it's what I always wanted to do in our timeline analysis work that we do. We use timeline data quite frequently in our investigations. It's a very important source of data, right? So forensics is, as we all know it's a lot of debugging systems or debugging behaviors in systems to understand what happened, right? And timeline helps us with that. So I got excited about that. But before we do that, I want to step back just a little bit, just for a little while, to talk about the data that we are using here. So at Google, we use another project called Plaso to get this data. So to do the research and to do the analysis and to solve our cases, we need the data. So we have Plaso to do that. Plaso is a framework. It started out as a small Perl script back in the days by that guy. And it turned out to be a bigger Python script, and now it's many Python scripts together in a system that is a framework of parsers. So we have a bunch of parsers there, 160 plus parsers to parse file systems, file formats, and whatever you can throw at it, right? And the output of this is timelines and timestamp events. We get a lot of them. So millions, like a normally used Windows system, you can get around 4 or 5 million events. That's not unusual. So you get a fair amount of data, and that's just one system, right? If you have then 10 or 20 or maybe 50 systems in an investigation, it kind of adds up, right? But Plaso is an amazing source of this. I won't go into detail of Plaso and how it works, but the developers are here today, so please reach out to them or us if you want more information around that. All right. So when I started a few years back, we still did processing on text files, basically. So the default output from Plaso is, and it still is, a CSV file. So when you do an output or an export for Plaso, you get a CSV file. Then you have a few options, right? Two of them. The first one is throw this in a spreadsheet, do your analysis there. Don't really scale that well. It can work for smaller timelines, but when you have tens or maybe 100 or million of events in your investigation, the spreadsheets start to get a little bit tired and slow. So the other part, and I'm not really a spreadsheet person in my analysis, so I kind of resort to my trusted tools, the text processing tools available on Unix systems, so ZGraph awk. This works pretty well for one-offs when you are analyzing small amount of data, or if you know what you're looking for. And to be clear, I still use these tools day to day. They're really good. They're really good at what they do, but when it comes to scalability, there's a little bit of a problem. So we needed another system for this. This is kind of how Timesketch became a thing. So Timesketch is a tool we're going to use today as the example of how to apply this research into the real-world investigations. So we figure out that we need another system, right? So two things, and this is what's been originally in Timesketch for a few years now, is number one is search. So we came to the conclusion that we need to be able to search our data. And to be able to do that, and the search should be quick, and it should be able to search the structured data we get from Plaso. So to do that, we experimented with a bunch of data stores, but we ended up doing this in a full text search engine to give that fast capability. And Timesketch being open source, we use open source data source, and then one we choose is Elasticsearch. And it works pretty well for us, for our use case, for the scale that we're using this. But the second part is collaboration, and that has also been from the start in Timesketch, like the collaborative features. That's why I was so happy to hear a couple of years back when Autopsy also started supporting multi-user case stuff, right? So you have a central database of this and working together, because that's what we found out. To be able to scale our operations, we need to be able to work together and collaborate. So collaboration features was a key thing for Timesketch when we started it. So this is just a screenshot of how that looks like. This is not a talk about Timesketch per se, but I just wanted you to see how it looks like. So within this interface, we can now work together on our timelines. We can support tens of millions of events per case. We can search across that. We can annotate data with comment tags, labels, stars, whatever the things you expect from a collaborative environment. So we have that, but that's not what we're going to talk about today. We want to talk about how to take the research that Kitty just showed us into an application like this. So to do that, and we stepped back and thought that, okay, we have the search and we have the collaborative features, and it kind of works in Timesketch. What else do we need to be able to scale and to be able to make it more fun for us to work in our cases, right? So if you're a system administrator, you kind of know this already, but it's kind of a mantra. If you do it more than once, you want to automate it, because the reason it's important to automate some of the grunt stuff that we do or the repetitive tasks is if you automate one thing, you get more time to automate even more things, and at the end of that line, you get more time to do the stuff that you actually want to do, and that is investigating, figuring out the case, solving the cases, right? That's what we want to do. We don't want to do repetitive tasks that machines are better at. So that's kind of what we saw, and we didn't really have this in Timesketch. It was still manual. We could work together, but still manual, right? So what we came up with is two more features in Timesketch that we needed to do. So the first one is what we call assisted analysis. And this is basically taking the repetitive stuff that is being done in most of our investigations and automate that in code. But the most important part, and that's the next feature, is we need to encode our knowledge, right? Because if we can reuse our knowledge that we get from research, apply that in a tool like this, and encode it, save it, and rerun it on all future investigations, then we save a lot of time, and we get more insights into our data. So those two things, and that's what we're going to talk about now, assisted analysis and encoded knowledge, and kind of how we have implemented that in Timesketch. And I want this to serve as an inspiration for other tools as well. How can we do this, and how can we share this knowledge, and how can we encode it to use it together in the community? All right, so a little bit more technical, but not too much. How did we implement this in Timesketch? What did we need to do, right? So this is a very, very high-level view of how Timesketch kind of fit, all of the different pieces fits together. But you have the data store in the back end there, and you have some workers for importing the data into those. What we built was a framework for analyzers. We call them Timesketch analyzers. So this is a framework that takes care of most of the heavy lifting for you infrastructure-wise. So when you import data, you want to be able to run a piece of code on that data to analyze it and maybe enrich your data, right? So we take care of setting up a task queue, making sure that tasks run in parallel when it can, so we scale them. We provide you, as a developer and researcher, with interfaces and APIs to make that simple, so you don't have to care about that. So that's kind of what we did with Timesketch. But we just want to make it work, and to make this a pleasant experience for you and the people who's going to use this, we just want to make it work, right? It should just be there. So we have three main use cases. The first one being the researcher, the unicorns. The second one being developers, because we need to write a piece of code to encode this knowledge, as I will show you. And the third one is actually the analyst, right? When we sit down in the tool and we try to solve our cases. So three use cases that we just want to make it work for. So the first one, if we start with researchers, and this is where it becomes interesting, right? Because bridging the world between the research platforms, Colab, Jupyter, for example, and Timesketch, we realized very early on that, hey, we can actually, what we probably want to do, we want to mimic as much as possible that we have in the research platforms already and support that in Timesketch. So most of the tools, libraries, visualization libraries that have been developed over the years that Kitty mentioned, they're all open source, right? So we can support them in Timesketch, and this is what we did. So we now have support for all of the scientific libraries in Timesketch, and we have support for the same visualization libraries, which means that as a researcher, you do sit in your research environment, you analyze your data, you get the data, you create visualizations, and you can be sure of that if either you develop that yourself and port it over, or you ask someone else to develop a piece of code to make that repeatable and usable in Timesketch, you know that what you have written and what you have done in your research environment can be ported over, basically a one-one mapping to Timesketch, which makes this way easier. So it's what you see is what you get kind of experience, right? Visualizations are important. We support those. Aggregations are very important. We have, this is to get the insights into your data that we all get from the research, right? So we have support for pandas, which is the de facto standard for data format from the libraries. So you can do aggregations there. You can do native Elasticsearch aggregation, expose those to your analyzer code as well. Or you can get a stream of events and do your aggregations in code however you want. So we have a very flexible framework within a framework, I guess, for aggregations and sharding. But in the end, and in the middle here, you see the code, and that's also portable over basically one-one. And we will see this example. I'm using the same example as the Fisher domain one and how this can look like in Timesketch. So there's another thing, and Kitty already mentioned this briefly, but there's another very important piece of this is data, right? So the data that we do research on should mimic or should it sometimes be the same data that we do in our analysis, right? So you want to be able to use and analyze and research the data as it is. So we have built and extended the already existing API client for Timesketch to connect to the research platforms transparently for you. So you just import that, you connect to your Timesketch instance, and you have your data. That makes it even more intuitive as a researcher and developer to do your research and port it over. That's very important. So as a developer, again, you can focus on writing the code or porting over the code that your researchers have done. So the heavy lifting is taken care of you. You will get a stream of events. You basically give it a query, you get a stream back, and you can do your logic on that stream and enrich Timesketch back, right? So what you get with the framework and the API and interface that we've built is whatever you can do manually in Timesketch, in the UI, you can now do programmatically. So you can add your comments, you can create your views, you can annotate and enrich the data as much as you can in the UI now in your Python code, which means that taking the logic out of research, you can take that, enrich the data on Timesketch, and get value out of it from there. And in the end, you can see there down there, we have emoji support, which is important. That is Kirst's favorite feature. He's the one adding all of the emojis, and tagging is support, and so on. So I just want to briefly show you how easy it is, and I kind of want to give you a little bit of inspiration how easy it is to get started with analyzers if you are keen on trying this out. So we have another project called L2T Scaffold. This comes from the Plaso project, which is basically a code generating program that generates templates for you. So if you want to create a new analyzer and starting encoding your knowledge, taking your research out in the real world, you can now use this program to kickstart that. So you run the program, you answer a few questions about what you want to do, and it will generate 2 files for you. One file is the actual code for the analyzer, which have a stub for an analyzer. The other one is tests. Tests are important, especially if we are analyzing data. We want to make sure that we are parsing it the right way, that we do cover all of the edge cases and so on. But what you basically need to do in an analyzer is this. You don't need to do much more. You have a query there, and you have a bunch of to-dos. To do, you need to just fill in the blanks, fill in the query that you need, and this is the query to give you the results and the events that you need for your research, or for your analyzer. That will give you a stream of events that you can operate on. This is where all the magic happens. This analyzer doesn't do anything, right? You have to add your logic, but you can. So now you have a stream of events, and each event you can then annotate back using simple methods like add a star, add a comment, or add a tag to that event if you find it interesting. And that's it. That's all you need to do to start experimenting with this and taking the research out from that part and put it into the real world. So the last one, to wrap this up, the last use case that we want to cover and that we are covering is the actual analyst, right? Because at the end of the day, you want to use this. So in Timesketch, this can look something like this. So if we take the example that Kirsti had with the fishy domain analyzer, which do all of this funky stuff with similarity and mean hashing and so on, right? At the end of the day, you want to be able to have that transparently just be there for you, having this assisted analysis being there for you to bootstrap your investigation. So what you get in that example is one link. Before you have even started investigating this, you go into Timesketch and you have a link saying, hey, you probably have fishy domains here, maybe you want to take a look at those. So the first thing you do, you click on that link and you go directly into your timeline. You have a way to pivot. As we all know who have done timeline analysis, you need pivot points in your data to continue and start your investigations. You get a pivot point to these fishy domains, and you see Kirsti's amazing emojis here. Of course, a fishing rod because it's fishing, as a death skull there because it's evil, I guess, and tags and so on and so forth. But the important point here is that the system helps you get into your timeline to find interesting pivot points. So you can then start by doing your manual analysis or collaborative analysis with your colleagues to continue that. And that's all of the heavy lifting from research to development, implementation, porting over to Timesketch. At the end result is I get a link to click, I get into my timeline, and I can do the fun stuff like investigating, right? All right, so to sum this up, and kind of if we wanted to have one thing after this talk to think about is we want you to be the unicorn. So we have you have the domain knowledge, right? You do forensics, you know all about that. That's what we do, that's our profession, that's our trade, right? You have that domain knowledge. Now you have tools, platforms, open source libraries, amazing tools like Autopsy and others to implement this, right? So you can do the research, you can get access to these tools and these methods and statistical models you can build out, right? Together with the domain knowledge that you have, you can do amazing things. And now you can also easily, looking at the example from Timesketch, for example, it's pretty easy to build this and port this over to applications that we use day to day as well. So I guess what we want to have to say, be the unicorn and start doing research and start porting that over into reusable knowledge that we can all use in the community. If you have anything, if you're writing analyses that are not internal to your organization, please send us pull requests. I'm happy to merge that into the main repository as well. And with that, I open up for questions.
Which we probably don't have time for.
We have no time for that. We have a disclaimer. If you don't have time for that, please reach out. I'm going to be here all night, so let me know if you have any questions. Thank you very much.